In this problem, we're given a realistic intensity pattern for two slit interference. And these tall, narrow bumps, those are the intensity maxima, but they're being suppressed to 0 by a diffraction pattern superimposed on that. That diffraction pattern is caused by the width of the slits themselves. It's a little hard to see the grid here, but right here I have 1 on the grid. Right here I have 2. Right here I have 3. Here I have 4, and so on. And this problem is a little different because we're asked to just observe this pattern and then work backwards and calculate the slit separation and the slit width. So in part A, we're told we're assuming we're using 633 nanometer red laser light, and we want to know the approximate slit spacing. Well, it's the interference pattern, in other words, the small bumps, that depend on the slit spacing. So I'm told the grid tells me the number of degrees that I'm seeing these maxima at. So this is at 1 degree I see a maximum, at 2 degrees I see a maximum, at approximately 3 degrees I see a maximum. So I can just go ahead and use that first off-axis maximum of 1 degree, plug into the interference formula. That's d sine theta equals n lambda, where n is equal to 0, 1, 2, and so on. N equals 0 corresponds to the central maximum at an angle of 0, so I'm not interested in that. What I'm plugging in is n equals 1 for the first off-axis maximum. Again, that occurs at an angle of 1 degree. And what we're trying to solve for here is little d, the slit spacing. So I'll get it symbolically real quick. And that's lambda over sine theta. Plug in the wavelength of the light in the correct units. Nanometers are 10 to the negative 9. And then the sine of 1 degree in the denominator. And I get a slit spacing of 3.63 times 10 to the negative 5th. It might be a little nicer to express this in microns or micrometers. And I get 36.3 microns. In part B, we're asked for the approximate width of the slits. And I see my first diffraction minimum occurring at an angle of 4 degrees. I'm supposed to have an interference max right there, and it's been suppressed completely to 0. So I know that my diffraction min is landing right on that 4 degree mark. And the formula for diffraction minima is a sine theta equals n lambda, where n is 1, 2, 3, and so on. And a is the width of the slits. So I solve for a. I sub in n equals 1 because we're talking about the first diffraction minimum. So a is lambda over sine theta. Again, sub in the wavelength in the correct units. Sub in the angle at which we're observing this diffraction minimum. And I get 9.07 times 10 to the negative 6 meters, which again is most appropriate to express in micrometers or microns. So I get 9.07 microns. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.